Hey students, in this video we are going to discuss how to write an equation for an exponential growth word problem and also an exponential decay word problem. Last week we did that exploration with the zombies and the March Madness problems where we kind of got into exponential growth and decay, and we're going to continue that this week because your test is on Friday. First, let's start with our equation y equals a times b to the power of x. We should recall that the value of a is our initial value or the y-intercept. We also should recall that the value of b is the common ratio. We can also think of this as a common multiplier since this is the number that we're multiplying by each time to find the next term. And with all exponential growth problems, the common ratio or the common multiplier is always going to be greater than 1. That's what causes the function to grow or increase rapidly. So as long as this value on the inside of the parentheses is larger than 1, then we know it's exponential growth. So before we get into this word problem here, I'm actually going to have you figure out what the equation is for this table and this graph, since we've been doing that for about a week and a half now. You have the option to write this table by hand, or you have the option of using a calculator, since I've shown you that as well. And remember, you can enter that in a list in a spreadsheet, which is option number 4. Type in your x values and your y values, and you'll just have to choose the option for exponential, since this is an exponential function. So I'm going to let you do that first, and that'll be your warm-up, and then we'll continue with the discussion to how we are going to write the exponential growth equation for this word problem over here. So now that you've written the equation for the table and the graph, this is what you should have got. So if you decided to write this by hand, you should have figured out that, hey, we're multiplying by 4 each time to go from 1/8 to 1/2, and we're multiplying by 4 to go from 1/2 to 2, and then times 4 to go from 2 to 8, times 4 to go from 832, and this is considered our common ratio or our common multiplier. We also needed the y-intercept, and we can get that directly from the table. That's whenever the x value is 0, so my y-intercept is 2. Similarly, on the graph, I went ahead and wrote down those values for you, and so we could make a table from this graph if you're going to do it by hand. And we can see that we're multiplying by 2 each time to go from 1 to 2, multiply by 2 to go from 2 to 4, and then by 2 to go from 4 to 8. And so this is my common ratio or my common multiplier. And my y-intercept from the graph was 1, and the y-intercept from the table was also 1. So this is my exponential function. Notice that both the 4 and the 2 represent the value of b, and that number is greater than 1, which is why this represents exponential growth. So now we want to look at the word problem, and we want to apply that same concept that we need to figure out what the initial value is and also what our common ratio, our common multiplier is based on the information being provided. So when we read this word problem, it tells us the population of a city grows at a rate of 5% each year. The city's population was 400,000 in 1990. And we want to write a function that describes the population of the city after X years, or I should say X years after 1990. So I put an extra after in there. That's like a little mistake. So I'll take that out. Well, in order for me to write my function y equals a times b to the power of x, I need to know 2 things. So we must know what the initial value is, and we must know what the common multiplier is. To find the initial value for this particular problem, well, that represents in a way, our starting point or the starting population. So the population, according to the problem, started with 400,000, or at least that was the population in 1990. So I can say that my y-intercept, or the value of a, is 400,000, so 400,000 people. And if I want to find the value of b, our growth factor, then we know that the city's population grows at a rate of 5%. So grows at a rate of 5%. That is telling me that the 400,000 represents 100% of the population, because that's everybody. and it's going to grow or increase. So we plus that 5% that it's going to increase by, which is 105%. Now, this next part is very important because that's not going to represent the value of B, because B is not a percentage. It's actually a growth factor, or a factor in this case. And so I need to turn this number into a decimal. And so to turn that number into a decimal, you can either divide it by 100, or you can simply move the decimal place 2 units to the left, so 1, 2, and that tells me that my growth factor, or the value of B, is 1.05. And so when we write our equation, it's going to be y equals, well, the value of A, we already said was 400,000, times the value of B, which is 1.05 to the power of x. And so we know that this is an exponential growth because the value of B that we've gotten here is greater than 1. And so we can actually use this equation, this exponential function, to figure out what the population is going to be in 20 years and 30 years, what we're expecting it to be based on the information provided. Now let's look at our second problem, the second real-world situation. But first, notice that with exponential decay, we have the exact same equation, y equals a times b to the power of x, where a is still the initial value of the y-intercept, and b is still our common ratio or common multiplier. The only difference that now b is a number between 0 and 1 for it to represent exponential decay. And so just like the previous problem, I want you to write the equation for the table and the graph, and you can use whatever method you would like. You can do it by hand, or you can use a calculator. And then I'm going to go over the answer with you just to make sure that we're on the same page. So with the table, you should have noticed that each time you're multiplying by a third, and that is the common multiplier or the common ratio. That's the value of B. And my y-intercept here, whenever x is 0, is 9. So this equation, y equals 9 times 1/3 to the power of x, that is my exponential decay equation for this table, because 1/3 is between 0 and 1. Similarly, just like the graph, we can see that the graph is decreasing at a rapid rate, which represents exponential decline. And if you make a table from the graph, you can see that each time we're multiplying by a half to get to the next value, and the y-intercept is 1, according to the graph and according to the table. So my exponential function is y equals 1 times 1/2 to the power of x. So we want to use this information when we talk about the equation that we can write for our word problem, just like we did before, y equals a times b to the power of x. I know that in the problem, the value of a is going to be the initial amount. So as you read the problem, it says the car was purchased for $18,000. Well, that $18,000 is the initial amount. That's the starting value of. Now, for us to figure out the value of B, well, we know that the car is depreciating according to the problem. And if you're not quite sure what the word depreciate means, it just means that the value goes down. So the value of B is going to be 100%, which that is the 18,000, but it's going to depreciate. So we're going to subtract 20% of the value every single year. And so this tells me that the value of B is going to represent 80% as a rate. But we don't want that to be a percentage. We would prefer, or we actually want that 80% to be represented as a decimal. So I know that I need to take this and move the decimal 2 places or divide by 100. And that way we'll end up with the value of B is 0.80 or 0.80. And now I can write my function y equals 18,000, which was the initial value. So 18,000 times that decay factor, which is 0.80 to the power of x. And so when we compare, this 0.80 is between 0 and 1, the 1/2 is between 0 and 1, and then the 1/3 is between 0 and 1. So each of these are a representation of exponential decay.